Right. Let's get right into it. So let's start with the motivation for our work. As you might all know, in recent years we have seen a steadily increase for high quality and detailed renderings with like the better hardware and better software each year we add. And on the other hand, we have devices like the Meta Orion glasses, which try to push the boundaries of small, low-powered, head-mounted devices that come with a few limitations, like limited compute power, also the ability to transfer and storing geometry for large and detailed scenes, and they might even not have any rasterization hardware. So the question is, how can we combine these two worlds to have high-quality renderings on such low-powered devices? And one obvious solution for this comes with cloud rendering, where we simply try to offload the rendering entirely to a high-powered server and then stream the results to the client, which simply can show the images. However, this, of course, kind of needs a low latency to work well, because the motion-to-photon latency can become quite bad if you have high latency, and therefore the movement of the head is simply too delayed, and that can lead to really bad perception. And especially with these devices that are connected over the internet, mostly in wireless, this is like not feasible in most cases. Same goes for the bandwidth. Streaming high frame rate, high quality videos in most cases simply isn't feasible. Therefore, recent works have explored the split rendering paradigm, where we try to divide the rendering work between the server and the client. In the simplest case, the server would simply render at a lower frame rate, and then we can use some simple technique like time warping on the client. However, especially for time warp, it only accounts for rotation of the head, but no translation, and also dynamic scenes are not accounted for. That's why recent works have tried to come up with better strategies, like Quad Stream by Radl et al., which use an approximate proxy geometry that can more easily be rendered by a low-power client. Or works like Xargo from Gao et al., which use a mesh-based reprojection to dynamically hide the latency. However, most of these works still need some kind of non-trivial geometry processing or do not handle dynamic scenes. And therefore, we propose a purely image-based method that does not need any rasterization hardware at all, can handle dynamic scenes using bidirectional reprojection, and also we handle disocclusions by using additional auxiliary cameras on the server, and we can also handle dynamic shadows. So let's start with what we are given. This is one of our example scenes that we use for evaluation, and this is rendered at 10 frames per second, basically what our server gives us. And now we want to upsample this to a higher frame rate. So how do we do this? Well, our method is based on the bidirectional reprojection method from Young et al., which basically introduce a 1-frame latency to reproject from 2 frames to interpolate and introduce new frames. And this leads to fewer disocclusions as we have more information. For this, they also generate a 3D scene motion flow field, which basically for every pixel gives the motion to the next and the previous frame in clip space. And they use these motion flow fields to perform iterative point search and find corresponding pixels in the T and T+1 frame. After this, they compare the results of both images, and in the case of 2 good corresponding pixels, they simply blend the colors. However, if you want to make use of this for a split rendering scenario, there are some challenges we have to overcome. First of all, the method is designed only for client rendering, which means that the start and end position is fixed of the camera, so we only have linear camera motion between two frames. However, we want to be able to react to the user's head movement during the two server frames that are sent. And they also only use temporal upsampling, no spatial upsampling. And since they can always guarantee to have the next frame, they also do not need any extrapolation, which for split rendering, where we might have some missed frames, is not possible. So, therefore, we propose to decouple the scene flow into the object motion only flow field, and the camera motion is then handled by the client. So the object motion is sent by the server to the client, and we then use this together with the current head position. This means that we need to recompute the forward and the backward scene flow for every intermediate frame, and of course deviating from the predicted head movement from the server does lead to new disocclusions and therefore holes in the image, and that is why we propose to also use additional auxiliary cameras on the server with a higher field of view and also a slight positional offset, which then fills these holes. So this is what the data would look like sent by the server that is used for the reprojection, where we have here the color, the depth, and the 3D object motion for the T and also the T+1 frame. Our algorithm then looks like this. For both the T and T+1 frame, we compute the scene flow to the current interpolation frame using the object motion sent by the server and also the current head position. We then split the scene flow to the current time step, so to the current interpolation frame, and use a 3x3 window search to find a starting point for the iterative point search, which we found that 3 iterations is then enough to find good corresponding pixels. Then we compare the results. We're using the reprojection error and also the projected depth, and then determine the best match. And again, if we find good matches in both images, we simply blend the colors. So if you do this, you can see we already get a higher frame rate, which looks much more fluent. However, you can also see that due to the head movement that deviates from what the server thinks is going to be, we also get some disocclusions that lead to holes. And this is why the third step of our algorithm is to also do the same for the auxiliary cameras. So if we do not find any good matches, we simply repeat the algorithm for the auxiliary cameras until we find a good match. Doing this, now we get rid of all the holes, and it looks much better. However, you might also notice, if you have a look at the shadow of the moving mannequin, that it still looks kind of funky. And this is due to the fact that we only track the object motion and not the entire optical flow of the image. And therefore, dynamic shading changes such as the shadows are simply not tracked and only get linearly blended, leading to the results you have seen. So the idea is to separately also track the shadow changes. So our first idea was to simply render the server at the same target frame rate as the client, and then have a per pixel bit string, which basically encodes for each interpolation time step if the pixel is in shadow or not, which, if we upsample from 10 to 120 frames, would lead to 11 bits per pixel, which is quite a lot. And also, this only works for hard shadows. Of course, for soft shadows, as you can see, this results in artifacts. Therefore, we decided to use more than 1 bit per intermediate frame, so per time step, which basically simply quantizes the soft shadow values. Of course, doing this for 120 frames per second would lead to a lot of data per pixel. So instead, we track the shadows at a decoupled frame rate that is not dependent on the color and server frame rate or the client frame rate. And we have found that 40 frames per second is enough to get good results. What I haven't mentioned is that, of course, to interpolate the shadow colors, we also need the minimum and maximum shadow colors that a pixel sees during the interpolation steps, and therefore we also have to send this additionally. This leads to more data, of course. However, as you can see, in most cases, this data is quite sparse, where here you can see example of what the shadow bit field, the minimum color, and also the maximum shadow color looks like. So the last step in our algorithm is to use the shadow information if there's any present for good correspondences. And when we do this, you can see that we finally get something that looks close to the ground truth. So in total, our pipeline looks like this. We have the server, which gets frequent updates, position updates of the client. Then it renders the data for the color, depth, and the object motion, and also the shadow information, and finally sends this data to the client, which uses the new data together with the data from the old frame and the actual current head position to render the intermediate frames. Of course, sending this much data does require some form of compression and encoding. Luckily, we are purely image-based, which means we can use widely adopted video codecs. For RGB images, we simply use 8-bit HEVC and can also do this with NVENC, of course. Then for floating point images, like the object motion and the depth, we found that 8 bits are actually too limiting in the precision and lead to significant artifacts at object borders. And therefore, we use 12-bit HEVC, which seems to give a good trade-off between compression and quality. We have one special case, the shadow bit field, which, of course, being a bit field, needs lossless encoding to retain the bit order, and therefore we simply use the standard compression, which gives a nice compression to latency ratio. For our evaluation, we used 3 scenes. First one here being Robot Lab. The second one you've already seen, the sponsor scene. And lastly, we also tested on a custom Viking village where we just added some random moving objects. For our setup, we used a 1440p camera, main camera with 60 degrees field of view. We also have 2 auxiliary cameras that render at a lower resolution, 720p, and have 80 degrees field of view. And they are also shifted to the left and the right of the main camera a bit to have some offset, and also they are slightly rotated outwards to cover more space. The server renders the color, depth, and object motion at 10 frames per second, and the shadow information at 40 frames per second, and the client upsamples this to 120 frames per second. Our camera paths for our experimental setup are predetermined and simply use animated paths. However, to simulate the delay of the user's pose, we simply generate the server frames at a 100 millisecond offset. The methods we compare to are simple time warp, a simple forward splitting approach, a re-implementation of the backwards bidirectional reprojection, which means that it basically does not react to the deviating client movement at all. And we also compare to our method with extrapolation only, where we basically simulate a missing frame from the server and simply use the negative backwards flow field of the last frame we have. For our setup, we basically have 3 components. The server data we generated using the universal rendering pipeline from Unity. The encoding and decoding was simply done using FFmpeg, and the client is implemented in C++ and CUDA. The communication in this case was simply done via the file system. So coming to some results, we tested every method on the compressed data using a fixed bitrate of 40 megabits per second, and we used the image metrics SSIM and Flip, and also VMAF as a video metric. And as you can see here, compared to the other methods, our method clearly outperforms the easier, more widely adopted methods. Especially time warp and backwards bidirectional reprojection, you can see perform quite poorly, which is mainly due to the fact that they simply do not align with the ground truth, as time warp does not account for translation, and also backwards bidirectional reprojection does not react to the client's movement. Now you can see some examples. This is what the time warp looks like. As you can see, due to only rotational adjustments, it looks quite choppy. The splatting, forward splatting, looks a bit better. However, the object movement does not look that good. And the bidirectional reprojection does look quite good. However, keep in mind that it does not react to the actual client head movement. And this is our method with extrapolation only. As you can see, it does perform quite well. However, the object movement does look a bit unnatural because simply extrapolating the motion is not as good as interpolation. We also did an ablation on the rate distortion curve, so we tested on different bit rates. You can see in green the ground truth, 120 frames per second, and the time warp in blue, which we tested at different frame rates, and our methods in orange, and also ours in extrapolation in violet. And you can see that we basically outperform the other methods at any bit rate. However, the sweet spot seems to lie at around 40 megabits per second. Coming to performance, as our setup was mainly designed for high flexibility to test this method, it is not optimized for execution speed yet. Therefore, the reprojection currently takes around 2 milliseconds per frame on an RTX 4090. However, we think that there's still a lot of potential for optimization here. In conclusion, we provide an image-based spatio-temporal interpolation pipeline for split rendering, which operates without the need of any geometry, so it's purely image-based. We allow for a free viewpoint, although we do assume linear object motion between frames. And also we're robust to the dynamic soft shadows. We can leverage widely adopted image compression methods, and our results do show a qualitative and also quantitative benefit over the comparison methods. For limitations and future work, we'd like to test this setup on a rear streaming setup, which should be quite easily to adapt. Also, currently we only handle dynamic soft shadows, but there are other dynamic lighting effects that we would like to see adopted as well, like caustics. Also, currently handling multiple light sources simply increases the data sent linearly, which I think can also be done more efficiently. And in general, this method might also benefit from a more custom optimization compression scheme. With that, I thank you for your attention, and I'm open for any questions now.
Thank you. Two very quick questions.
Thanks, nice talk. You addressed shadows and mentioned caustics as another lighting effect. I'm curious if you have thoughts on how this might handle reflections or like transparency.
Yeah, that's another thing. Like reflections again is also not handled currently, so that's also something that would be nice to explore in the future.
Hi, I was wondering about what happens if you're on a moving platform. So it seems you're only sending objects, motion vectors. So if the camera's moving, then it's not like the head movement of the headset. But if you're on a moving platform or in a car or something like that.
Oh, you mean like you're with the headset on something moving, like a train or something?
Yeah. You're on a moving platform that takes you around and that would generate motion.
Yeah. I guess that's kind of a common problem. In this case, it depends on what the headset actually sends, but if it's just the pure motion based on, I don't know, some GPS data or something, then of course this would lead to problems, but it's probably something you would have to keep in mind, like with normal sensors like having IMUs and stuff like that, it usually leads to some kind of problems.
So thank you. We are a little bit behind time, so I would defer further discussion to the coffee break. I have some burning questions myself. Let's thank Thomas again.
All right.